Well, hello again. Well, immediately after free radical substitution, I am doing this hopefully short clip as well. Maybe not as short as the other one. There is a bit more to mention because now we enter into the area of isomerism as well that requires a little bit of explanation, further explanation. Addition. You see, in the previous reactions with free radical substitution, the word substitution came in. You know, it's like football, that 11 players on the pitch. When one goes in, only on the basis that one goes out. They substitute each other. In chemistry, in many cases, we have substitution reactions. But what about addition reactions? In addition reactions, things just, the name is quite clear. They just add themselves across. When we talk about fuels, burning fuels, always saturated hydrocarbons, the alkenes come to mind. Alkenes certainly don't. We don't burn alkenes because we can easily add things to them and turn them into something far more precious and useful than just burn them for fuel. So, addition reaction, but electrophilic addition reaction, what happens here? Let me give you an example. At GCSE level, I'm sure you did simple tests to identify alkenes and alkanes, tell people which one is which. And you use bromine, or rather bromine water. You added it to alkanes, you added it to alkenes, and when you added it to alkenes, the distinctive orange color of bromine disappeared. And that's all you needed to know. But imagine at this level, you need to know what actually happened. So imagine you've got an alkene, carbon double bond. So you have hydrogen, 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 and let's say R, where R could be anything. Yeah, if it's hydrogen, is ethene. If it's CH3, is propene, etc. Right? So we don't worry about that. And imagine we want to react it with bromine. Now, if you remember your intermolecular forces and London forces, where we would not have expected, things can actually become polar as a consequence of uneven distribution of electrons. Do you remember I explained that as part of modules 2 and 3 before? So we can write bromine next to this molecule as a polar molecule. And usually how we write it is like, if you write your alkene horizontally, it's best to write your bromine vertically. And then you show polarity as well. So that end is partially positive, whereas this end is partially negative. But there is something else I want to tell you as well. Don't you agree each bond is 2 electrons and therefore double bond is 4 electrons? So therefore there's an area of quite a lot of electrons. Electrons have negative charges, and the electrons around bromine also have negative charges, and therefore these electrons kind of repel the electrons from one end of the bromine to the other end. Partially, not totally, of course. And that is referred to as its polarizing properties. It actually polarizes the bromine even further, making it delta plus, delta minus. So we don't just need to rely on intermolecular forces and London force in order to explain why bromine becomes a dipole. But nonetheless, this is the situation. Now, if I use a different color, so arrows in showing the reaction mechanisms, arrows, remember this, because a lot of times some students make mistakes here, come from where the electrons are there to where they want to form a bond. So let's say that carbon wants to form a bond with that bromine. Of course, bromine cannot have 2 bonds. So when it forms a bond with either of these carbons, and I explained to you whether it matters in this case or not. Then the other bond breaks and deposits its electrons on that bromine, turning that into a bromide ion. Now let's imagine the scenario is as follows. So you have your carbon there, you have your hydrogen there, you have the R group there, and now, which color did I use? That one. And now you have that bromine sitting over there. Then you have the adjacent carbons sitting next to these hydrogens, these two that they were there. But now, because the electrons have been taken away from that carbon over there, that carbon becomes positively charged. What I tell my students is that consider that bond as if it's a door and the hinge is over there, and therefore if it opens like that, right, like for example it does in this case, that carbon is forming a bond, taking its electrons as well as the electrons belonging to the other carbon, right? Which means that carbon is stripped off an electron, therefore is now positively charged. It becomes a nucleus or carbocation. So what happens to this one? Remember that bromine has now turned into a bromide ion. You can either show that with a lone pair or the negative charge, but your arrow has to come correctly, exactly from where the electrons are to where they want to go, right? You can, previously you were only allowed to take your arrows from lone pairs. Now you can take them from the negative charge as well. They would be, but you cannot draw them from anywhere else. Arrows come from where electrons are to where they are going to. Are they making a bond or breaking a bond? They must come from where the electrons are. And then of course, you end up with a dibromo compound. So hydrogen, hydrogen, hydrogen R, and then you have a dibromo compound. So going back to the GCSE years, when you added bromine and its color disappeared, because bromine, of course, is intensely orange, right? Even if it's diluted down in water, and therefore it's referred to as orange, bromine water. But when it is added across a carbon-carbon double bond, you can clearly see that this molecule, this compound, had all the elements that it originally had, 3 hydrogens and 1 R group, as well as 2 carbons. It still has them. But on top of that, now it's gained two bromine as well, hence addition. This is not substitution. But why electrophilic addition? Because these are partially positively charged. When things are partially positively charged, what do they seek? What do they want? Electrons. So there are electrophiles. In Latin means electron loving. So there are electrophiles. And so what do? They add across. And therefore electrophilic addition. I think if you can put electrophilic in brackets, sometimes even if you wrote addition reactions, it would still be accepted to, as a 1 mark answer. But it is correct. In my opinion, it is only correct if you refer to it as electrophilic addition. Now, I better proceed to another example very quickly. So let's say that you have this scenario here. And instead of bromine, you are adding hydrogen bromide to this molecule, propene. Hydrogen bromide. Well, hydrogen bromide is a permanently polar molecule, isn't it? Because it is made from hydrogen and bromine. Of course, bromine is far more electronegative than hydrogen. So this end is going to be delta negative, quite obviously, and hydrogen is going to be delta positive. Now, wouldn't you agree with me? Let me put the hydrogens here as well, so that you know that this is not something else. Wouldn't you agree with me that if that hydrogen added itself to this carbon, then that carbon becomes positively charged and you will produce 2-bromopropane. But if you added that hydrogen to that carbon, then this carbon becomes positively charged, so you produce 1-bromopropane. And they are each other's structural isomers. Right? So, again, going back to that door and hinge I was telling you, is this bond opening like that? Or is it opening like that? So there are two possibilities, and therefore in electrophilic addition, when it comes to addition with, say, hydrogen bromide, the examiners can actually include isomerism there as well. And not only that, they can ask you which isomer is the major product, which I'll come to in a minute. So let's consider this scenario, therefore. Let's say that carbon, so the two possibilities are, so if I, just to speed things up so you don't get too bored, you have that carbon that turns into a positive charge, and then that into 3 hydrogens. And therefore, the bromide ion will attack that one to produce 2-bromopropane. Agreed? But alternatively, if I can use a different color, alternatively, you can have this situation, hydrogen, hydrogen. And then the bromide ion will attack this one to produce 1-bromopropane. Yeah, just including skeletal formula, just to remind you that we've done these things before. But which one is the major product? These are both each other's structural isomers, if you remember isomerism, structural isomerism. There is this guy who's called Markovnikov, or Markovnikov's rule, right? And he said that hydrogen attaches itself to a carbon which has more hydrogens. That one. Which means bromine is going to add itself to that particular carbon. So this one would be the major isomer. And therefore this one would be the minor. So you produce 80% of the time that is produced, 20% of the time this is produced, for instance, right? That will not suffice if you just wrote that on your exam paper because Markovnikov said so. That is not a good answer. Because they ask why, and the why is because just before the final product, that stage is called the intermediate stage. That intermediate stage is more stable than the other intermediate, that intermediate stage. The reason is that the alkyl groups, this is a secondary, whereas that is a primary alcohol. If the tertiary would have been even more stable. The alkyl functional groups, methyl in this case, and either end of the carbon, have what is known as, they have electron donating capability, yeah? And they stabilize the carbocation more. Carbocation wants electrons, and these two side groups can actually provide a bit to stabilize the intermediate stage, and that is what you have to say. You don't say Markovnikov said so. You can say, according to Markovnikov rules, hydrogen adds to the carbon with higher number of hydrogen atoms attachments because the intermediate is more stable, and that is a very good answer, right? Now, why is it more stable? That again, that's the next level up. Because the functional group sitting on the carbocation are electron donating, or they have a positive inductive effect. These are the kind of things that I discuss with year 13s. All right. So now you have come across a situation where addition, electrophilic addition is taking place, resulting in isomerism. Enormously important as well. Remember your reaction mechanisms. Remember arrows. I've already mentioned it a few times. come from where the electrons are. You draw them from anywhere else, you just lost the mark. All right? Okay, thank you.